All right, welcome back, ladies and gentlemen. Hope y'all are doing fantastic. We are going to continue a video lesson today as we finish up 1.3 part 2. A lot of the same goals as part 1. We're just going to kind of expand what we know about our functions and look a little bit more today on some transformations. So let's take a look here at example 5. It says go ahead and graph the function. Now this is assuming we're graphing it not using a graphing calculator. And so let's go ahead and graph first and foremost here. So obviously this is our basic x squared or squaring function, basic parent function here, x squared. And then that minus 2 on the inside is our idea of a transformation. And if you remember correctly from your previous classes, when we have transformations that are on the inside of the parent function, like minus 2 is here, remember it's the opposite of what you see. It's always the horizontal representations that are the opposite of what you see. And so even though this says negative 2, this is actually moving to the right 2. So this is taking our original parent function and moving it to the right 2. And then it says on what interval is the function increasing, and then when is it decreasing. And so in this case here, we are going to be increasing at 2 onto positive infinity. All right, so that's going to be our increasing. And then our decreasing is then going to be the opposite then. Then it's going to be from negative infinity to positive 2. That is going to be our decreasing there. And then it says, is the function odd, even, or neither? Remember, odd symmetry means, or an odd function means its origin symmetry. An even function means that it has symmetry over the y-axis, and then neither means that there's just some other kind of symmetry, or there's no symmetry at all. So to test this, if you remember correctly, we go ahead and we replace all the x's with a negative x and simplify. And so at this point here, you can clearly see that just replacing that x is not going to give me exactly what it started off with, right? It's not going to give me anything the same because we didn't make a change here in the negative 2, and then we didn't actually get a negative x. If you wanted, you could go ahead and expand and FOIL all this out for both of them. But I think it's a little extensive, as you can kind of just tell that once you multiply things by a negative x or you multiply things by a positive x, it's obviously not going to give you the same result there. But the negative and the negative, when they multiply by each other, they would give you the same, and so you're not going to have any symmetry for that one. And again, if you want to clearly see that, you can FOIL both of those problems out and take a look at that. And then the last couple of questions says, does the function have any extrema? Does the function have any extrema? Well, obviously at this point right here, right, we do see that we have a absolute minimum. So we have ourselves an absolute minimum at x equals 2, obviously at y equals 0. And then here we have, how does the graph relate to the graph of the basic function? So this is just basically asking, well, what is the ultimate transformation? So what we did is we went right 2. We went right 2 units. All right, on to our next one, which we kind of increase a little bit of the interesting level. I think so, because you're dealing with piecewise functions here. So again, I challenge you to pause the video when these examples come up. Try to give them a shot on your own. But this one says, which of the 12 basic functions has the following piecewise function over separate intervals of its domain? And so this is kind of interesting. It says, which of the functions is a positive x for all of the values in which x is greater than or equal to 0, however, has a negative x to show that it is less than 0. So if you kind of just think about this in a sense, what think about this piecewise function. It's broken up into two separate entities, but ultimately what we're saying is that there's one function in which this is true. Well, if you kind of take a look here, what does this resemble? Well, hopefully you see that this resembles our absolute value function. So that's all that this really is, right? This is our positive x's for everything being greater than or equal to 0. This is our negative x's for everything that is less than 0 here. So this right side of the graph, that's this top portion of our piecewise function. And then the left side of the graph is the bottom portion of the piecewise function. And now obviously when you actually take the absolute value of those, it remains positive for the y's in both cases. That's why we're above the x-axis when you draw your absolute value function there. But then ultimately, what they're looking for is that you could also rewrite this piecewise function as the absolute value of x. So I find that kind of an interesting problem there. All right, let's move on to example 7. And again, see if you can go ahead and pause the video before I go over the example in and of itself. So this one says, let's use basic functions to construct a piecewise definition of the function. And so as you've kind of recognized, a lot of the functions, you can actually create a piecewise function out of it. And that's what we're going to do here. Now, this isn't one function, this is multiple functions. But if you kind of look here, here's obviously 0, right? And then to the left of 0, it looks like it's maybe one function, right? There's a certain type of one of our 12 basic functions that it kind of resembles to the left of 0. And then as to the right of 0, it looks like it might be another type of the 12 basic functions there. So again, hopefully you gave it a shot to kind of figure out what it may be looking at here. But in this case, it looks like that we have a function that's to the left of 0. Well, this kind of looks like a quadratic function. This looks like a parabola on to the left. So as we make our piecewise function, let's go say x squared. We're going to say that it's x squared from everything that is less than or equal to 0. Again, it just kind of looks like right here that point is including 0 in this case. All right, let's get including 0 in this case. So we're going to call the inclusion of 0 for the x squared function. Well, then what about the right side of the graph? Everything that is greater than 0. All right, so when x is greater than 0, what is that going to represent there? Well, hopefully you can identify that that kind of looks like our square root function in this case. It's kind of our square root function. And so to the right of 0, we would have the square root of x. So here's how we can construct a piecewise function based on, all right, two separate basic functions that are in here. And at some point, we'll be able to actually create those piecewise functions, not using just the basic functions, but be able to do them using transformations and stuff as well. All right, and then our last example of the part 2 is this analysis. And this is what we've been kind of leading to in the end of everything. If you remember correctly, I said the purpose of going through all of the 9 characteristics in 1.2 was to be able to fully analyze a function. And that is what we are talking about here. And so again, pause the video, give it a shot on your own and see if you can fill in all of these blanks that I have, and then see if you can go back over and see how you did. But obviously here, if you were just given the graph, right, it'd be important to obviously understand that if it was not provided for you, that this is the graph of the absolute value function. The domain in this case obviously comes all the way out here to negative infinity and all the way to positive infinity. So all real numbers. Again, you could have put negative infinity to infinity and fine. Well, what about the range? Well, clearly it's an absolute value function, so there's no negative values for that y. And then so you go from 0 all the way to positive infinity. And then it's a continuous function. I can go over the entire function, see that it is continuous. I don't have to worry about any points of discontinuity there. It's going to be decreasing from negative infinity to 0, and then it's going to increase from 0 to infinity. Obviously, it's going to be an even function because if you plug in a negative x, it provides you the same value in return, and it is symmetric about the y-axis, so it's an even function. You could say that it is bounded, but not bounded fully, it's just bounded below. It's asking for some local mins and local maxes and things like that. So you would say that you have a local minimum, in this case, at 0, 0. That local minimum would actually be its absolute minimum as well, too. That local minimum would actually be its absolute as well. There are no what types of asymptotes? There are no horizontal asymptotes. And then there are also no vertical asymptotes in there as well. And then last but certainly not least, the end of behavior. So as I'm approaching positive infinity for my x's, I'm approaching positive infinity for my y's. As I am approaching negative infinity for my x's, I'm approaching positive infinity for my y's. And so that's what we're looking at here is what are you doing when you approach negative infinity? I'm going to positive infinity. What are you doing when you approach positive infinity? You're also going to positive infinity for the y's. All right, so that's going to wrap it up for 1.2. This tiny URL is the step function. All right, this is our step function. If you want to go ahead and analyze the function by inputting this into your graphing calculator and graphing the step function there, you're going to have to make some changes. You don't necessarily have to graph it in your calculator. If you don't want, you can just look at the function in your 12 basic function beginning of these nodes. But if you want to, here are the directions up top as to how to plot the step function into your graphing calculator. Understand that you have to be in dot mode when you do so, so please make sure you're in dot mode. And then go to the tiny URL. This will be part of your attendance for today, and make sure that you complete the following domain range and the full analysis of the greatest integer or step function there.